Okay, let's talk about the next part of this lesson, which is equilibrium of a particle in two dimensions. This is our first real use of statics. We've been dealing with vector stuff already, but this is really static equilibrium. This is statics. This is why you're taking this course. This is 2D particle equilibrium. Can there be 3D? Absolutely, and you're going to do it next module, but not today. Okay, we're going to do 2D first. It's simpler. This is a 2D force system. All of these cables that you're seeing here lie in the plane of the page, so it's two-dimensional. It just makes it a little easier is all. There's a ring here at B. There's a cable going from A to B. There's a cable from B to C going up at this 25-degree angle. And there's a 50-kilogram load hanging down from B. If you built this with string or rope or whatever, I think you know that this would work. If the whole assembly is in equilibrium, then all of the parts are also in equilibrium. That's really important to how we approach statics. If we know that this thing is not moving, then we know that none of the parts inside are moving. And when I say moving, I technically mean accelerating, but they're in static equilibrium. We use that in statics, throughout statics. We're going to be drawing free body diagrams. We're going to isolate a part of the structure and realize that it's also in static equilibrium, of the entire structure is in static equilibrium, and so we can apply these equations of equilibrium and solve this stuff. Okay? So, free body diagrams. You've looked at them before. Okay? Free body diagrams, but it's the single most important thing for you to master and use in this course. The students, almost invariably, the students that have the most trouble that come and see me and say, I just don't get this. I'll be like, let me see your diagrams. And they're usually not drawn, or they're just very basic diagrams. I urge you, I beg you, I plead with you to please draw these diagrams and draw them at a size that is useful to you. Don't block off like a square inch of the page. Give yourself a few inches in each direction so you can draw, so you can label stuff. It really is how engineers solve problems. You'll need it to succeed in this course. You'll use them if you go on to strength of materials or fluid mechanics or any of those courses beyond. You'll also be using them. So you really need to get this concept down. And the reason you need to get it down is because free body diagrams are crucial to being able to write the equations of equilibrium, which is the next step. That is the statics. Okay, we have to draw the free body diagram so that we can get the statics, equations of equilibrium. Okay, here's my 3 rules to drawing a free body diagram. And I made these up. They sound really basic. I like that they sound basic because then they stick in your mind. There's really a lot that goes on with these very basic statements. So don't scoff at their simplicity early on. Realize that as long as you absolutely and utterly follow these 3 rules when you're drawing a free body, you will learn to let free body diagrams work for you as opposed to something, free body diagrams being something you have to draw. A lot of students are like, oh, he wants me to draw a free body too, just to get credit. Oh, that's such a bummer. Really, the idea is eventually you'll realize that the free body diagram is how you can then see how to solve the problem. Okay, the first step is going to be keep the part that you're keeping. Okay, so we're drawing a free body diagram at point B, right? We want to find all the cable forces in this system with this 50-kilogram load. So I'm going to keep the part that I'm keeping. I made my cut here, here, and here. This is an equilibrium of a rigid particle. It could have been tiny. This particle is so small and all these forces are concurrent. It doesn't matter that I drew a little bit extra, but whether this length here is 1 angstrom or halfway across to the other end, it doesn't really matter. But this is equilibrium of a rigid particle. Keep the part that you're keeping. So I kept the ring. I kept this little bit of cable here, a little bit of cable here, a little bit of cable here, and I kept that 25 degrees. You need to label all of your dimensions here. And an equilibrium of a particle, it's all going to be angle dimensions. So you're going to have 25 degrees up from here. These I don't have labeled because they are obviously horizontal and vertical. If they were at angles, you would need to label those as well. Get rid of the part that you're getting rid of. Everything else goes away. And at the cuts, you put the internal forces that will develop. So I have a tension force here I've drawn, and I'm calling it FAB because this point over here was A. So this is the force in cable AB. This is the force in cable BC. I don't know what those forces are, so I gave them labels. I gave them variable names. This one down here, if you recall, it was a 50 kilogram load or 50 kilogram mass. So 50 kilograms, if you multiply by 9.81, is 490.5 newtons. I never write kilograms on a statics free body because it has no point there, because remember, mass is a scalar, not a vector, so if it's pointing down like it is here, this has got to be a force, all right? So 490.5 newtons acting down. So when I cut away all this stuff, I replaced it with these internal forces that are happening. So now I can develop my equations of equilibrium. Now that I have this free body, things should be pretty obvious. I have a couple of equations of equilibrium. Realize that this is statics. There are no net forces and no acceleration. So I know that the summation of forces equals 0, not MA. It's 0. So I write all of my forces on one side of my equation. I set that equal to 0, and then I solve for my unknowns. What are my unknowns here? Well, I have FAB and FBC. This is a known value. So let's pick which one we're going to do first. Well, if I did sum of forces in the x equal to 0, I'd have FBC times the cosine of 25 degrees minus FAB equal to 0. That's no good because I have two unknowns. So I know a lot of people would think x first because x is the first one. You usually think x and then y and then z. In this case, for this problem, you would do y first because you could isolate this unknown. See how this one's acting purely in the x. I have the x going as positive to the right. I can do sum of forces in the y equal to 0, up positive. So this business over here is saying that the up arrow is then positive. I write that every time because I want to, it's like a mantra. I write this whole thing every time I write in real life with pencil. I would write sum of forces in the y is equal to 0, and I would say up positive. Because now I'm being very direct with myself. I've stated I am summing forces in the y, so I won't have any x forces in there, right? It makes it easy for me to go back and check my work, and it also keeps me honest when I write my work. So here I have FBC, but it's not acting in the y. Its y component is, which is this side over here, SOHCAHTOA. That means it's going to be the sine of 25 degrees. So I have FBC times the sine of 25 degrees. This vector doesn't come into play. FAB does not come into play. But this one does. So minus 490.5, it's negative because it is down, and positive y is up. So I have FBC sine 25 minus 490.5 equals 0. Like I said, I like to put everything on one side of the equation, equals 0 on the other, and then solve for my unknown, which is this. And I get 1,161 newtons. And so that then is the value for FBC that you see up here. I write it on my free body. So that I can then look at my free body and say, okay, what else can I find? Well, obviously now this is my next unknown, and I can use sum of forces in the x to solve for it. Okay, this is kind of a basic free body. Sometimes there's a lot more going on. So, you might have been like, I didn't really need to write this up there. Maybe not for this one, but I would urge you to do it until you get the hang of it because, especially in multi-step problems, it will help you if you write what you've learned in step 1. That will help you figure out what step 2 is for that free body. So step 2 is going to be sum of forces in the x equal to 0, going to the right positive, and I have 1,161 newtons because that is now a known. It's no longer unknown, right? 1,161 newtons times the cosine of 25 degrees, triangle trig, SOHCAHTOA. That's going to be the adjacent over hypotenuse. And then minus FAB equals 0, so FAB is equal to 1,052 newtons. All right, and I can write it up there, and now my free body diagram is complete. Things I would note about this: don't try to say FBC x component, right? Always leave it in terms of the full resultant and multiply it by its trig. Because if you put in the x and the y, what you're really doing is creating a bunch more variables that will make your life hard to deal with. Leave it in terms of the magnitude, multiply it by the trig to get it to, the y component is FBC times sine of 25 degrees. This whole term here is the y component, but I'll leave my variable in terms of FBC, and when I solve for it, that is the value of this vector as drawn. Okay? So that's a good way to write it. And then, like I said, keep populating your free body diagram with the information you get as you go. This one I probably wouldn't even have written myself because I had already gotten everything out of the free body that I needed. I was no longer going to use this free body. I might have gone on to a different free body if I had multiple points I could make free bodies of. In this system that we have here, there's not, so it's a little bit simpler. But you might not write the last step up there. You've got them down here. So to pull in the last few things here for this topic, oddball things, I guess, but these are things that you've been exposed to before. A spring, remember, it has a spring force that's equal to the spring constant times the deformation of the spring. So if you're given a spring and it has a spring constant that you're given and you're given the deformation, guess what? You know the force in that cable or that rope that the spring is in line with because you're given that value. So that is the internal force. So that's one value you can already check off your list of things to solve for. And then pulleys. Pulleys, completely separate from springs, but you get the deal. Frictionless pulleys. If you have a frictionless pulley, then you know that actually T1 and T2 are equal to each other. The cable passes over the pulley and doesn't lose any of the internal force. It changes the direction of the vectors. Okay, so the magnitude of T1 is equal to the magnitude of T2. Now, their location, their directions are different, and you'll have to deal with the vectors as the problem needs to solve. But you already know the magnitude, which is a huge, huge win. That is only really true for frictionless pulleys, but that's the only kind of pulley that we're going to use in this class. So, as life goes on and you want to deal with friction-full pulleys, pulleys that have friction in them, you certainly can, but it's just going to be a complicating factor. We're not going to deal with those in this class. So if I say a pulley, it's a frictionless pulley in this class. So that's it for this lecture.